Good morning, dear colleagues and guests. Thank you for joining us for InnoDays webinar 21, Green Hydrogen Fuels and Electric Propulsion in Shipping. InnoDays events are a sequence of seminars and webinars organized by Motus Foundation and co-organized by Actia Forum, dedicated to the latest in maritime, transport and ports, digitalization, as well as energy and alternative fuels. I am Emil Amrowski, Managing Director of Motus Foundation, and I will lead you through the presentations today. Well, today's webinar will focus on the fossil-free green hydrogen-based fuels and ammonia, also electric propulsion and charging infrastructure for ports, vessels, and maritime transportation. The webinar's partner is Technik, a Waptec company, which offers innovative electrification system for ports and vessels. Presentation on behalf of Technik will be given by Mr. Rainer Altmeppen, a segment leader for ports and maritime. We will start with the presentation soon, and our fellow speakers today also include Mr. Grzegorz Pawelec from Hydrogen Europe, Mr. Adam Niklewski, a regional expert on alternative fuels at DNV, and Dr. John Kokarakis, a technical director at Bureau Veritas. After a short break following the first presentation session, we will continue with the discussion panel. The discussion panel will be chaired by Mr. Bogdan Ogrodakowski, a Secretary General of Baltic Ports Organization, and Ms. Maja Felicia Benstead, Chief Business Officer BAUK at the Port of Rhone, will join the speakers in the panel as well. The panel will concentrate on the future production, supply chain, and logistic of green hydrogen-based fuels, and the actual port's role in this supply chain. So I would like to also mention about our supporting partners. So we've got Baltic Ports Organization, our main supporting partner, and media partners, Gospodarka Morska, and Baltic Transport Journal as well. The event is organized by Motus Foundation and Actia Forum. And from my side, my last words at this time is towards our participants from all across Europe today. Please share your comments and ask your questions to our fellow speakers and panelists today by using the chat section in the YouTube channel. Questions will be forwarded directly to our speakers and presenters, and they will answer them. Okay, well, without further delay, I would like to invite our first presenter today. It's Mr. Grzegorz Pawelec from Hydrogen Europe, who will give us a presentation on opportunities for hydrogen, considering the European Green Deal. Grzegorz, if you can hear me, yeah, I can see you. So you may start your presentation now. Thank you.
Yes, I hope you can hear me as well.
Yes, we can hear you.
Share my screen quickly. Full screen. Okay, I hope you can see everything fine.
Yes, we can see it now. Please.
So indeed, I will focus a bit on what's the role of hydrogen specifically as a fuel for shipping. as well now, as in light of the recent regulatory proposal by the European Commission for shipping sector included in the Fit for 55 package. Just to start, a couple of words about Hydrogen Europe. So we are mainly a business association which represent currently more than 300 members active in the field of well, broadly hydrogen, but not every hydrogen. We focus mostly on promoting clean hydrogen, so either green or any other let's say production technology for hydrogen, which leads to substantial reduction of CO2 emissions. And the main goal is complete decarbonization of our society. So that's something that maybe makes us a bit different than the usual trade association. We not only speak with the voice of our members, but we have, let's say, a mission of our own, which is clearly to promote hydrogen as a solution for decarbonization. To start about the fuels itself. So over the course of 2019, we have, together with our members, developed, let's say, a techno-economic assessment tool to look at various options based on hydrogen, and to compare the costs of implementation of those hydrogen options for various types of ships. So we have looked at both the straightforward options like compressed hydrogen or liquefied hydrogen. We have looked at liquefied organic hydrogen carriers, or a bit more kind of complex fuels, like if you combine hydrogen with hydrogen with nitrogen to produce renewable ammonia, or you can combine hydrogen with a sustainable source of CO2 to produce synthetic fuels like synthetic LNG, synthetic methanol, or even synthetic diesel. And then obviously you also have a number of various different options of how to reconvert that fuel back into energy on board of a ship. So we can use internal combustion engines, which are already well developed as a solution, or you can look into the more emerging solutions like PEM fuel cells or even solid oxide fuel cells. Each of those have their own strengths and weaknesses. For one, as I mentioned, the fuel cells are a bit less in terms of technological development. They have substantially lower TLR than combustion engines, but on the other hand, for example, if you use synthetic fuels like ammonia and a solid oxide fuel cell, you don't need to crack that ammonia back into hydrogen, as would be the case in PEM fuel cell, for example. And if you choose your catalyst rightly, there is no air pollution whatsoever. So even if you use synthetic methane and a solid oxide fuel cell, also you can completely avoid air pollution, which is not possible, or at least extremely hard to do with a combustion engine without some after treatment systems of flue gases. So already you can see here that there are plenty of options, and this does not even include biofuels or batteries or anything that's not related purely to hydrogen. And in fact, this multitude of options is a problem in itself, because it kind of stops investors from investing, it stops ports from investing, because I mean, it's hardly difficult to understand that a ship owner is not really willing to invest in a ship that's expected to last for 20 years if he's not sure that the fuel that he chooses for that ship will be available in 5 years' time, for example. So clearly we need to start eliminating those options and looking which makes sense long-term and which doesn't make sense long-term. And that was the main purpose of this exercise that we did together, as I mentioned, with our members. So it's not only an internal analysis. So the conclusions were, let's say, the main one was rather straightforward, but it's still quite important, I think, to repeat it as often as possible. And the fact is that there is a trade-off kind of relationship between all of those fuels. So when you look only at cost of fuel, compressed hydrogen and those other pure hydrogen options are always cheaper than the alternatives. So and that's a bit of a no-brainer. I mean, if you have to do additional steps, like, for example, capture CO2, synthesize the hydrogen with the CO2, and then maybe also liquefy it to produce synthetic LNG, no matter what your expectations are about how renewable energy costs will shape in the future, what will be the electrolyzer capex or any of that, no matter what your expectations with this are, the pure hydrogen option will always be cheaper than those synthetic fuels. It will just be always the case. Huh? But on the other hand, when you look at energy density, then the relationship is exactly the opposite. So the pure hydrogen option, like compressed hydrogen, has the worst energy properties out of all of those hydrogen-based synthetic or alternative fuels. And then there is this trade-off that for various ship types, when you look at ship types that can refuel often and don't need to carry a lot of fuel on board, the fact that the compressed hydrogen is the cheapest is the factor that is the most dominant in choosing which fuel to go for. And if you look for ships that need to, cover the whole Atlantic or Pacific on a single tank, then the value of this energy density difference becomes the biggest factor in deciding for which fuel to go for. And then obviously the synthetic fuels make the most sense. And if you apply this kind of trade-off or analysis, looking at costs, to various ship types, this is basically what we found out, that if you look at various short sea shipping applications, so small ferries, ships that operate within ports, then compressed hydrogen has some role to play. It is as I mentioned, the cheapest fuel. The energy density of it is not that big of a problem, so it comes out as the cheapest fuel, the most optimal one in terms of cost for ship owners. And by cost, I mean also the value of lost cargo carrying capacity of a ship. And then if you look at the other extreme, so ships that indeed the ocean going, the deep sea shipping vessels, there it's the synthetic fuels that indeed are the cheapest option. And out of those synthetic fuels, it's always ammonia that is the cost optimal one. And that is simply because it doesn't require this additional carbon molecule, and nitrogen is substantially cheaper than CO2. And then everything in between, we found that there is quite a lot of space for liquefied hydrogen, which gives you this kind of a good optimal balance between the cost of fuel itself and the energy density of the fuel. But if you actually look at number of ships in operation, how much fuel they use, if you try to, let's say, divide this analysis into market share, you end up with a result that shows that 90% of the all fuel consumption for all 90% of all ships, maybe not all ships, but in terms of volume of fuel consumed, 90% of the market would go to ammonia in this case, and around 10% to liquid hydrogen, and only a small portion to compressed hydrogen. That's only half of the story, as I mentioned. This only shows which option is best out of the options which are based on renewable hydrogen. But obviously, the ship owners don't only have these options to choose from. There is also the benchmark, which is the heavy fuel oil or marine gas oil. And all of those options, even the cheapest ones, are still quite substantially more expensive than the incumbent one. And here you can see what would have to be the CO2 price in the ETS system to let's say, to make the fuel switch financially viable on its own. And this is also based on let's say, 2030 projections of what we have in terms of green hydrogen production cost. If you would look at this graph, today's costs, it would be not twice as high, but at least 3 times as high in terms of the difference between fuels based on renewable hydrogen and marine gas oil and heavy fuel oil. So what this shows you is that considering the fact that the current ETS price, even taking into account that the prices of it are record high at the moment, it's still around 50 euros per ton. And in order to kind of force the fuel switch, we would require an ETS carbon price of around 150 to 200 euros per ton for most ships. So what this shows you is that clearly just the proposal of the Commission to include the ships in the ETS is not enough on its own. But fortunately, The European Commission has, I think, recognized that fact, and they have included a lot more in the Fit for 55 package in terms of proposed regulations that would impact this whole relationship. First, other than the ETS, okay, let me maybe start from the left. This break-even point now, this is basically what I said. So we would need hydrogen at 0.9 euros per kilogram today for it to make sense as a fuel for ship owners. And that's clearly not possible. That's even very hard to do with hydrogen based on natural gas, not even talking about green hydrogen, with production costs in Europe around 4 euros per kilogram for green hydrogen, even excluding all the logistics of transportation, port, bunkering costs, and all of that. So clearly there is still plenty of room, plenty of funding gap or financial gap that is there currently. So what the European Commission has proposed is that they have proposed to tax the maritime fuel a bit higher than it's the case currently with the Energy Taxation Directive. This would add some 10 cents per kilogram of hydrogen to that break-even point. Then there is the ETS, which I just mentioned. It's not enough, but still it's already 0.5, 0.6 euros per kilogram of hydrogen that you could produce it a bit more expensively to reach the break-even point. But then there is the Fuel EU Maritime Regulation, which imposes targets in terms of reduction of greenhouse gases intensity for each ship, or ships can be pulled into kind of grouped into a pool, which then the pool itself is being evaluated. But still, there are some targets that you need to reduce your emissions. And if you would look only at that, let's say, market niche created by the target, so within this small area, the penalties for non-compliance are so high that this would add around 5.5 euros per kilogram of hydrogen to that price. So if you combine all of those regulations that are proposed in Fit for 55, you could theoretically make a positive business case for using hydrogen as a shipping fuel, even if that green hydrogen would cost around 7 euros per kilogram. So this is quite high. This is achievable even today. And will be, of course, even more achievable in the future. So on one hand, this for us is a extremely good direction that the European Commission has proposed, because indeed, at least for this portion of the market that is related to the targets that the Commission sets, obviously for the remaining fuels that fall outside of the target, you will still face only the ETS and ETD benefits, so that would still make hydrogen quite too expensive. But if you combine it also with the penalties from Fuel EU Maritime, there is a niche on the market developing where hydrogen can indeed play a role. But there are a couple of problems with that regulation that we feel. First of all, there is no specific sub-target for zero-emission fuels like hydrogen options. And what this means is that hydrogen will, and other zero-emission options like electricity, for example, whatever, they will have to compete with everything else on an equal basis. So on one hand, I very much like the technological neutrality principle, but the fact that options based on completely fossil fuel solutions like fossil LNG, for example, they could easily get you to achieve the -2% or -6% target by 2030. And if you don't then have a sub-target for zero emission options, this puts it a bit in question whether the ship owners will even start looking at those options before 2030, 2035. And basically that's the other problem with those targets, that if you indeed open it for all technologies to compete on equal footing, then we feel that those targets are quite not as ambitious as they could have been. Because I mean, indeed, LNG is good enough to reach the targets by 2030, set up by 2030. So that's not as ambitious as we think it could have been. And then also we feel that there is a small loophole there, which allows to use OPS, so onshore power supply, and claim that it is zero emission no matter what the actual carbon footprint of that electricity was that was used. So you can put a LNG power plant on shore or even coal power plant on shore and supply ships with that electricity and still claim it's zero emission. So, and given the fact that, for example, cruise ships, a lot of the total energy consumption throughout the year is actually energy consumed while at berth at ports. If you take into account that they can claim all that electricity that they will charge from shore as zero emission, if you combine it with maybe they will run on LNG, they could easily not have to do anything else in terms of action towards reducing their emissions, even as far into the future as by 2035 or 2040, just through the fact that those kind of loopholes exist in the FuelEU maritime regulation. So again, we at Hydrogen are quite happy with the way the Fit for 55 has developed and the regulations that are there, but still, I think at least one of those three problems that I have outlined here should be removed, because otherwise we just feel that the regulations that have been proposed will not be as impactful as they might have been otherwise. And yes, that was my last slide, so I'm happy to take questions either from you, from the panel, or from the audience. Thank you very much.
Grzegorz, thank you for the presentation. We appreciate it. You're available for on such a short notice to give us a presentation based on hydrogen and the future of the hydrogen green-based fuels. As you wouldn't be able to join us for the panel session later on, thank you for including these slides for the Fit for 55 impact on the hydrogen fuels. It's very interesting to see your and Hydrogen Europe overview on that. But I would like to ask you a question, short one, on the how do you see the logistics and future production and eventual supply chain in the future, and considering maritime transport? Mainly, what do you think? Is there any solution to avoid the situation what was with LNG at the beginning, when it was very slowly developing? It was keep on coming these complications with chicken and egg situation. What is first? What is the second? What is important? So is there any solution which can help the hydrogen-based fuels to overcome these problems what at the beginning LNG had in the maritime ports and the shipping segment?
Yeah, that's a very good question. To one, I unfortunately don't have a clear answer for, in the sense that I don't think there is a simple solution to that problem, because it's indeed a huge one. So compressed hydrogen, obviously there is, it's not difficult to do it, but the problem there is that, I mean, if you want to transport it by trucks, basically one truck takes 400 kilograms on a single go, and that's way too less for any meaningful ship. So you need, and that problem was also there for LNG, and it's many times worse for compressed hydrogen for shipping. So you would need to have basically a pipeline going directly to a port for that solution, or only use it for very small ships. When it comes to liquefied hydrogen, then obviously there is a lot to learn from the LNG sector, but here we face also a problem that kind of not only is it, let's say, a bit lower in terms of TRL when it comes to large-scale tanks and all of that, but even in Europe we have very little liquefaction capacity. We just have a couple of plants with only 5 tons per day of liquefaction capacity, which again is way too low for that fuel to start making a big impact. But not all is so bad. I mean, when we look at ammonia, for example, as a solution, there are a number of, let's say, good things going on for that solution, in the sense that this is already a world traded commodity. There are already many tankers that can carry ammonia. There are already plenty of maritime terminals that can be used to ship ammonia, or there are already many storage capacities developed inside ports that can store ammonia in ports. So ammonia itself already has some good, let's say, starting position. Obviously, much more would have to be done because those, let's say, terminals exist only in places where there is a ammonia production plant nearby. So in Poland, that's probably only in Police at the moment. But still, already there is some, let's say, backbone of that infrastructure available to be further developed for that particular fuel. But clearly, this is a huge problem which we recognize, and that's why I also feel a bit that the alternative fuel infrastructure directives revision that was proposed by the European Commission is also a bit of a missed opportunity in the sense that it does not require any fixed obligation in terms of having either LNG or some type of alternative fuel bunkering infrastructure to be built up in maritime ports.
Yes, thank you, Grzegorz. Thank you really for those, well, a very concrete explanation and how do you see the future. Once again, we see underlining the ammonia, it has a slight advantage in it. So thank you, Grzegorz, for joining us. We are sorry that you wouldn't be able to stay for the panel. Thank you again, and I hope to see you soon on another of our events. So I would like to move forward on our presentations today. And now I would like to invite Mr. Adam Niklewski from DNV to give us a better overview on all these hydrogen-based fuels in shipping. We are concentrating on maritime, so it will be great. Adam?
Yeah, good morning, ladies and gentlemen. Yeah, I will confirm if the presentation is clearly visible.
Yes, we can see it.
That's perfect. Yes, I'd like at the beginning to thank you, Mr. Grzegorz Pawelec, because I truly believe my presentation will be complementary to what he said. So big thanks for this opening to Mr. Grzegorz. But going straight to the topic. Before I go directly to the maritime sector, I would like to say some words on a general energy transformation, because we can't treat maritime without the all view external context. Definitely the electrification and the hydrogen-based fuels, this is the connected factors. We need to be aware that the global energy system is electrifying rapidly, and what we expect in the next 30 years, the electrical power will be double in 2050. What we need to also to mention that nowadays the fossil fuels have held about 80% share of the global energy mix and that is for a long time. And this position will be gradually lost. What we could expect by 2050, the fossil fuels will be responsible only for the half of the energy consumption and the energy mix globally. What we could also observe, of course, the hydrogen will gain the position year by year, and what is also worth to mention, somehow the last 2 years of the pandemic, we a little lost. Let's say maybe it's not a lost chance, but we lost a number of opportunity because the huge volume. The huge funds has been given to recovery the current economy components, and it was not able to invest in the future zero emission solution. So as well, what is also important when we consider the external factors, we need to see what is going on the electrovehicle market, which definitely move and motivate the electrification. However, we also need to understand that some of the sectors like maritime and aviation, they are actually hard to electrify, especially when we consider the deep sea shipping. So what we could see, and this is a compliment to what Mr. Pavelec said, the future will go in the maritime sector with the hydrogen, of course, the combination of the e-fuels and the biofuels as well. What is next, I'd like to say, and it's also a kind of complementary information. We have nowadays a pretty nice development on the solar energy and the wind technology, which means that the technology cost is already competitive. The same story it's about the already mentioned in the electrovehicle sector. But when we look on the hydrogen, we are a little bit behind these ones, and if not much the higher efforts given, what we expect, the competitiveness of the hydrogen technology will be ready in about 10, maybe 15 years, closer to 2040. Yes, what was already mentioned, the hydrogen solutions can be implemented in a different consumption way. Of course, this is the internal combustion engine, and that means the monofuel and the dual fuel, and as well the fuel cells technology, which we can't miss when we consider the hydrogen and hydrogen sourced based application. What we can see on the current slide, and I will give you some examples. Nowadays, we have some already demonstration project or limited number of already set in use solutions. Starting from ammonia, which was already mentioned. Of course, this is very, very promising solutions when considering different factors, not only the transportation, but also as a middle carriage of the pure hydrogen as a chemically bonded. Of course, ammonia can be used in the both kind of propulsion, so it can be used in the internal combustion engines and the fuel cells itself. So in that case, we are a little bit behind, even compared with the hydrogen. And nowadays, if we look and take away the LNG and LPG, the methanol and the e-methanol version, the application is already on the market, and it's about 28 vessels in operation. So about the hydrogen sources. On the current slide, we can see the different source of the hydrogen production, and what is the most important where we are here. Nowadays, unfortunately, we are missing the green hydrogen, and that's only spots on the blue hydrogen production. There's 2 facilities. So main production sources are the fossil fuel based, mainly the natural gas and the carbon itself. But it will be exponentially change, and as we can see, the electrolysis process as a production source will become a significant part, up to taking 50% of the market at the 2050. What else? That of course will impact on the fuel mix in maritime sectors. And what we can see here was the energy consumption drop due to the COVID, but then we will constantly grow and go for a little bit flattened curve, which comes from the efficiency of the applicable technologies, and of course the regulation, which will also require this change. What else we can observe? The low carbon fuels, which contains all of the solutions like hydrogen, synthetic MGO, synthetic LNG, and ammonia. And then we have the electricity, which will of course take its role, especially in the shore shipping. And what we can see, the LNG and the LPG will dominate in the sector of the fossil fuels. However, what we could see comparing to the 2019, nowadays we are gaining the momentum, where the transformation in the maritime shipping definitely speed up. So it's, when we look on the new order books, it's double in 2021 comparing to the 2090. And what we could see, of course, still the LNG is a dominant part. The battery is growing. However, the methanol solutions definitely take this position. And unfortunately, hydrogen and ammonia are a little bit behind. Of course, each of the fuels have its pros and cons, and this matrix presents in a, I believe, quite easy to understand way. So green means very positive aspects. Yellow, it means the average, and the red ones are rather on the lost position. So maybe the we will only say a couple of words on the current fossil fuel based. Of course, the energy density, price, maturity of technology, infrastructure, everything is in place. So this is green, but there is no green credential at all, and that will definitely be changed. But when we look on the hydrogen, we have a lot of works to be done on the infrastructure, on the technology part, on the availability as well. The pricing, this is the different story, and clearly explained by Mr. Pavelets in the presentation before. However, the green credential on the hydrogen and the hydrogen-based fuels are definitely the future. The ammonia, it's a little bit better if we are talking about the infrastructure. There is also already a lot of experience in the transportation of ammonia. The pricing is a little bit better position, and then energy density. But the technology, unfortunately, the same step behind the other solution. What was also mentioned, and I hope this graph shows quite significantly the volumetric density of compared energy carriers. If we take as a single the reference the very low sulfur fuel oil, then the LNG we need 2 times more space, LPG about 1.5 to 2. The methanol still compromising for a deep sea trading with a 2.5 volumetric space. But then we go to the ammonia and the hydrogen, which significantly change the and impact the design of the vessel. And here we can see on the example visualization, the ammonia tanks is rather located on main deck of the vessel, and it is very significant space needed for that. Of course, there are some way of compensate that. One of them is, of course, the shorter bunkering intervals, the increased amounts of the pilot fuels, or just blending the carbon neutral and the fossil-based ones. Regarding the costs, the capex of the capital expenditure which has to be invested depends on the expected growth, the economic growth, and the same parallel the maritime sector transportation needs. If we are in a low growth curve, we see a little bit flattened distribution of this cost. However, it's a lot of the investments compared to the business as usual nowadays. Of course, that's pretty much depends how it will goes with the pricing distribution on the fossil fuels and renewable fuels, and of course the biofuels, which are the third alternative. If we go for the very high growth in a transportation needs, including the maritime sector, it's even explode much higher. And of course, this cost has to be somehow covered, and then we could, I believe, discuss in the debate about the taxonomy and any other kind of assentiveness to for the ship owner. What we could also need to consider when discuss the future of the hydrogen implementation, we need to consider the growth of the price of the electricity and the capacity of this electricity comes from the renewable sources. So depends on how the production will develop, and of course how the maritime sector needs will go together with that. We could see that this, for example, blue and the gray numbers shows what will be the participation of the maritime sectors in the general economy energy mix needs. So definitely it will go together. And as I said at the very beginning, the electrification and the alternative fuels in the maritime sector, these are the very connected topics. And the other point, the carbon capture and storage, which especially is mentioned when we are talking about the any kind of the synthetic fuels like e-methanol, e-LNG, e-MGO. Then we need to consider the carbon capture, which will eliminate and has to be combined together with these fuels to keep them as zero emissions. And at this stage, I'd like to mention as well that the carbon capture and storage capacity plan in 2030 is about 200 million tons per annum for the general economy. And honestly speaking, I would like to give you the two numbers. If we consider fully fully captured CO2 from the steam methane reforming process of the hydrogen, we need 775 million tons per annum. And if we would like to decarbonize by the carbon capture the full maritime sectors, we need an 800 million tons per annum. So there is a lot of infrastructure investments to be performed just to meet these needs. I'm just look on the clock, so I'm on the right track to meet my time. So the hydrogen value chain for shipping. For the future, of course, the electrolysis process, so the electricity generation mainly from renewables, wind farms and the solar panels. Then we need the transportation, which means the pipelines or the hydrogen carriers for the longer distance, and that's very limited due to the costs and unfortunately boil off the hydrogen with its boil temperature at minus 223, and then the utilization after all in a propulsion. What is also worth to mention, we have two options for utilization of the hydrogen as a propulsion. The one is the internal combustion engine, and then we need the cleanness of the hydrogen at the level of the 97%, and that gives the direct implementation of the hydrogen produced from the fossil fuels. And if we are talking about the fuel cells, then we have a very high need for the purity of the hydrogen, and that can be achieved only in the hydrogen electrolysis production process. Of course, the use of the hydrogen, it's been already described in a couple of ways. So maybe two additional factors. If we are talking about the compression of the hydrogen, we are talking about a minimum 350 bars. So this is a very high pressure, up to 700 bars. For the liquefaction, the temperature is, of course, the cryogenic technology with the temperature around and below 253 Celsius grade. If we are talking about the hydrogen, in principle, SOLAS and IMO allowed the application as in the way of the alternative design. So there is no yet the rules set up in place. The basis is that for the alternative design, that's the safety, reliability, and the dependability of the system shall be equivalent to that achieved with the conventional oil fuel. machinery and auxiliary machinery space. So nowadays, the solutions directly with the hydrogen, it's only to be considered in that way, which of course limited the easiness of the design of such solutions. And what I'd like also to mention for the hydrogen, the fuel cells, there is a high variety of the fuel cells solution. But what we could observe, the solid oxide fuel cells and the polymer fuel cells, they are the most promising. The other one is molten carbon fuel cells. And what is also worth to mention, the solid oxide and molten carbon, this is the fuel cells with which are the high temperature ones. So there is also a chance to cogenerate the not only the propulsion, but also the heat reuse on board the vessel. So this is a very promising solution. And what is nowadays on the market, we have a couple of, as DNV, a couple of the pilot projects with the hydrogen, liquefied hydrogen on board. And the first one was the Viking Lady, which was on test 10 years ago. And nowadays we have the Hydra ferry already in operation. But also what is worth to mention, the DNV together with the EMSA work together and on the studies on the fuel cells and this and the pollutions comes from that. So this is available on the EMSA sites. So you are free to look on that studies. Regarding the latest in operation, the Hydra ferries, as you can see, it's in the DNV class, and the fuel cell ready. The basic parameters: 80 meter length overall, with the breadth of the 70 meters, and it's rather the shore connection. Of course, this is the hydrogen fuel cells and the battery backup, and the type of the fuel cell installed on board is a polymer one. So definitely for the hydrogen in the maritime sector, we need to invest in the fleet of the hydrogen carriers, and of course for the hydrogen-based fuels, we need as well the fleet of the CO2 carriers. So the CO2 capture has to be somehow transported to the permanent storage and the further reuse in the synthesis of alternative synthetic fuels. And what I would like to leave you at the end, let's say the very optimistic and the very future-proof pipeline on the hydrogen, considering maritime sector, the renewables, and all the other players in the market needs a lot of investments in the infrastructure connection of the key players and involved parties in the market, so that we meet actually the Paris Agreement in 2050. At this stage, I'd like to thank you for the time and given a chance for the presentation, and I hope we will have some continuous discussion at the end in the second part of today's meeting.
Yes, thank you. Mr. Niklewski, for the very extensive presentation covering all the possible hydrogen fuels in the future and solar solutions as well. We appreciate a comprehensive presentation. Please stay with us for the discussion panel. Of course, we'll have some questions for you as we are moving quite fast now on the agenda. I would like to invite our next presenter. This is Dr. John Kokarakis from Bureau Veritas, who is going to underline us the future of ammonia as a maritime fuel. So the stage is yours, Mr. Kokarakis, please. If you can unmute yourself, put a microphone is on mute, please. Yes, that's good now. We can hear you.
Okay, very good. So good morning, ladies and gentlemen, and greetings from Piraeus, Greece. It is my privilege today to talk about this very interesting subject, and my presentation will highlight some studies and research related to ammonia as a marine fuel and the challenges associated with its use as a ship fuel. Why ammonia? Because we talk about hydrogen-based fuels. Ammonia is the largest carrier of hydrogen, having about 17% weight in hydrogen. The whole rainbow is represented in the production of ammonia. There are three types of ammonia depending on production. The typical one made with the Haber-Bosch, the celebrated Haber-Bosch method, the brown ammonia with a lot of carbon dioxide emission, about 1% of the global carbon dioxide emission worldwide. This is produced from hydrogen obtained from fossil fuels like reforming the natural gas or coal with superheated steam and also nitrogen. Blue ammonia is the brown ammonia, but accompanied with carbon capture during its production and, of course, subsequent liquefaction of the produced carbon dioxide. Last but not least, we have green ammonia, which is produced from renewable sources of energy sustainably with zero carbon dioxide emissions from renewable electricity, air, and water. Ammonia can also be produced in more exotic ways, like from biochemical synthesis, from photosynthesis of the cyanobacterium anabaedae, also in solid temperatures and pressures, directly from hydrogen from water and nitrogen from air in a fuel cell. What is noted here is that the Haber-Bosch method requires high pressure and temperature, and this is expensive. Ammonia is not subject to the chicken and egg dilemma because there is already experience in its handling and transportation. There is established infrastructure with 120 ports worldwide equipped with ammonia trading facilities. It is mildly cryogenic with a boiling point of minus 33.5 degrees at atmospheric pressure. Slow revving two-stroke engines are very appropriate to burn slow burning ammonia. Today, ammonia production is 180 million tons, primarily utilized for fertilizers. Ammonia has saved the world in the past by utilizing it in the production of fertilizers and avoiding famine and other problems in the food chain. Is viewed as the a compound that will save the world again to avoid the climatic change. It is easy to liquefy and transport with an energy density comparable to that of methanol. In order to serve the world fleet, we need a production close to 5 times higher than what we have today to satisfy the needs of shipping. Energy density is relatively low side, but it presents no risk of fire or explosion. The next 2 slides are presented for comparison with other fuels and for your quick reference.
I'm sorry, Mr. Kokorakis, I'm really sorry to interrupt you, but we cannot see your presentation. Will you be so kind to try again to share it?
Yes, I will try that. You cannot see it.
No, it's just the share screen option
Yes,
on the bottom of the panel.
I did.
Yeah. And after that, you need to select the exact presentation and click share button.
Can you share screen?
Yeah, share screen. You click on the actual presentation.
What about now?
And then share.
Yes, but can you see it now?
No, I cannot see it. Let me. What about now? No? No, I'm afraid it's still the same thing. It just after you press the share screen, the green button at the bottom, then you need to select the presentation from the panel which appears and then press the share button on the bottom right.
Okay, let me try something else because I have 2 screens and that creates problems here, maybe.
Yeah, I remember
So
yesterday on the test, it was successful. It will be much better if you can see your presentation.
What about now?
No, the same issue.
I don't know.
Okay, well, I'll suggest you continue further then. Of course, it's very interesting to hear about the opportunities of ammonia.
Well, I don't know what to say. This is the first time it happens. I follow the procedure. I share it. It is in the second screen. And
there you go. We have it now. Excellent.
Okay, so I'll go fast through the slides. I will not repeat the.
Yeah.
Okay.
That's perfect. You can take it from here. That's excellent. Thank you for that.
Okay, we discussed about this. Thank you for telling me. So as a reference, I include these 2 tables with comparing the properties of various fuels. What is important for ammonia is that it takes higher volume, as was mentioned by the previous speakers, than diesel because of its lower density and lower calorific value. It's about 3 times, I computed 3 times more storage space with a penalty on dead weight and cargo capacity. Regarding the price issue, of course, green ammonia is more expensive. Brown ammonia is actually lower. The price is about $250 to $300 per ton. It's fluctuating, but green ammonia is definitely over $800 per ton, which is a problem. But the fuel for fit for 55 proposal by the European Union will actually promote the utilization of green fuels. The key points for ammonia are that the target is to produce ammonia from renewable sources, and it seems that these are available. It does have better energy density volume-wise than hydrogen, with very high ignition temperature. It is this high temperature that causes the need for pilot fuel for the combustion of ammonia in internal combustion engines. Same is true for hydrogen as well. So technically, we cannot talk about carbon-free fuels when it comes to ammonia and hydrogen, only in fuel cells, only when it's utilized in fuel cells, as it was mentioned by the previous speaker. It can also be utilized in gas turbines and fuel cells. It is corrosive and highly toxic. It attacks carbon manganese or nickel steel. The attack is catalyzed by oxygen, temperature over minus 20 degrees, and high yield strength of the steel. Mixed with water, it becomes heavier than air, and it can reach the crew. It corrodes copper, brass, zinc alloys, and rubber components. We need to have detectors for in the redundant mode, and take care of ventilation and pressure relief systems, as well as remotely operated valves. The pipes transporting ammonia need to pass from a distance over a fifth of the breadth away from the collision-prone zone of the vessel and not go through manned crew spaces. The combustion properties of ammonia are, if ammonia is alone without any blend, we need a compression ratio of about 35 to 1, which is actually very high. So in order to reduce that and make it feasible, we blend it with either hydrogen, diesel, gasoline, or another hydrocarbon. The NOx emissions that are produced from its combustion need to be abated. The combustion of ammonia has the disadvantage of having very low flame speed, about 2 orders of magnitude lower than that of hydrogen, and high ignition temperature, but high knock tolerance. The difference with hydrogen is that hydrogen has also high ignition temperature, and this is the reason we need a pilot fuel, but its flame speed is higher. Inevitably, we have NOx, the typical problem in our exhaust gases, which needs to be abated because nitrogen is a component of the fuel. Formation of nitric dioxide, which is also known as laughing gas, it may be possible, and this is a problem because this is 300 worst from the global warming potential compared to carbon dioxide. We need to provide, first of all, select SCR, select catalytic reactors, or exhaust gas recirculation for the abatement of NOxes, or even scrubbers that will withhold the laughing gas with heterocyclic carbenes. There are various combinations, as mentioned, and propulsion options that can be utilized for ammonia. 4 of them are depicted here, like ammonia with hydrogen doping in spark ignition engine. We cannot use hydrogen in spark ignition engines, in compression ignition engines, because of the possibility of explosion. So in that case, we utilize a different pilot fuel like MGO or gasoline or kerosene. Also, another option is ammonia with proton exchange membrane fuel cell, battery and motor combination, or ammonia with solid oxide fuel cell and motor. The motors provide electric propulsion, and of course, there are many, many more options. Ammonia, looking at the spark ignition engines, ammonia and air are mixed in the intake system, inducted into the cylinder and compressed by the piston. A spark plug initiates combustion via an electric discharge at the end of the compression stroke. Ammonia can be a monofuel with hydrocarbon pilot or with cracked hydrogen. When we say cracked hydrogen, we take the hydrogen from the dissociation of ammonia. It is very typical, very usual, but only in spark ignition engines. Ammonia has a very high octane number and there will be no knocking. The slow flame front of ammonia can be improved with chemical doping with hydrogen, blending in ammonia up to 20% hydrogen by volume or 3% by mass, improves stability and avoids misfires. So hydrogen is an ignition promoter. It is also used these days in LNG, named high-thane. The blend is called high-thane to reduce methane slip. Looking at the technology available today, in the two-stroke area, MAN evolves the ammonia engine and the fuel supply system from the LPG the engine, the LGIP engine. So here we look what is proposed for the fuel supply system, and MAN provides the fuel at the required temperature and pressure of about 70 bar. It separates the return fuel from possible pollutants carried from the engine and can operate the purging when needed. The system can also minimize the release in the atmosphere down to safe conditions. It can be installed on the deck and connected to the engine by a double-walled piping to minimize the risk of accidental release. Fuel supply system consists of fuel preparation room with the supply pumps and the nitrogen purging system, the knockout drums, fuel valve train, and the storage tank. Low pressure and high pressure fuel supply system with return from the engine and supply at about 70 bars. The fuel valve train and the double supply pipe within the engine room. Now, looking at the fuel cells, these are devices where we have electrochemical conversion of energy, which is stored in the chemical bonds to produce electricity. They are very attractive because this happens with only one energy conversion, so fuel cells can attain very high efficiencies of the order of 60% or higher. Ammonia can be used directly, or ammonia is cracked into hydrogen and nitrogen, and the hydrogen is used in the fuel cell. Two fuel cell options are proton exchange membrane fuel cells, which you see in this animation, using purified hydrogen, and the other option is solid oxide fuel cells, using probably directly ammonia. Ammonia can be endothermically decomposed into nitrogen and hydrogen with energy from the exothermic oxidation and the water formation. Why we do not use then only fuel cells? The reason is that to do this to do this exercise, we need catalysts, and the catalysts are very expensive. The solid oxide fuel cell, a few words, is an electrochemical conversion device also that produces electricity directly from the oxidation of the fuel. It has an electrolyte, which is solid oxide or ceramic electrolyte. Oxygen ions are going through the electrolyte, reach the anode, where we have oxidation, which produces electricity, 2 electrons, so electricity, water, and heat. That heat can be utilized to disassociate the ammonia. The handicap of these solid oxide fuel cells is that it requires very high startup times because of the high temperatures involved. So instead, we have a change, we have the proton exchange solid oxide fuel cells, which is a variation, but with lower efficiency. Where do we stand from the regulatory standpoint? The most critical issue here is that ammonia is toxic, so the IGF code prevents the burning, the combustion of a fuel which is toxic. So IMO needs to impose regulatory changes in order to have application of ammonia as a marine fuel. Of course, all classes, and Bureau Veritas is no exception. We have our own rules for ammonia vessels. At this point, we have the minimum requirements for ammonia prepared vessels in preparation for the 2-stroke MAN engine. Wärtsilä has to be mentioned. They experiment with a 4-stroke engine, burning a blend of ammonia with 30% MgO and ammonia. Still, we have lower carbon dioxide emissions. Critical points are to take care of the design of the bunkering stations, the storage tanks. Remember, we need more space, the fuel handling system, the management of the boil-off of ammonia vapors, drainage, vapor treatment, and the venting. We participated in a workshop as recently as 2 weeks ago at the MAN, where we looked into the fuel supply system and the hazard associated with it. What we do in this case when there are no exact rules is very typical, instead of prescriptive rules, to utilize the risk assessment. So in a feasibility study we compared the high pressure LNG system, the MEGI diesel, with the low pressure Otto cycle WinGD XDF LNG engine and an ammonia. Here, the problem we had was that the OPEX for ammonia was skyrocketing because of the 800 tons per ton associated with green ammonia. So there is hope that in the future, when increasing the scale of production will reduce the price, and also with the incentives from the Fit for 55 and also other incentives, that the ammonia will become an attractive alternative fuel. Thank you very much for your attention. Apologies for the initial glitch with the presentation. I'm available for any questions you may have.
Dr. Kokarakis, thank you for the presentation. It was well worth it, the actual slides, so we really appreciate that. Please stay with us for the discussion panel, and if there is anything you would like to share additional, you have the opportunity there. Well, with that presentation by Dr. Kokarakis based on the future of ammonia as a marine fuel, I would like to close the first session of today's webinar. We will continue after 10 minutes. So at 10:30 Central European time, please join us for the second session of our webinar today. Thank you and see you soon. Dear guests, thank you for joining us for the second session of our webinar, Green Hydrogen-Based Fuels in Electric Propulsion and Shipping. We would like to continue further with the topics and the discussion panel. We will have now a presentation on behalf of our main sponsor today, which is Stenman Technic, a WAPTEC company, which is offering innovative electrification solutions and systems for ports and vessels. We'll have a presentation on behalf of Stenman Technic by Rainer Altmerben, and then we will have a discussion panel with our fellow speakers, which presented early on today. So without further delay, I would like to welcome now Mr. Rainer Altmerben to give us a presentation on the shore power supply and charging infrastructure for ports, ferries, and other vessels operators. Rainer, if you're here, I can see you.
All right.
Yes, the stage is yours. Please give us your presentation.
Yeah, thank you very much. I hope you can all hear me okay. And,
yes, you can see it. Yeah.
Wonderful. And first of all, thank you from Germany for the invite, for the opportunity to speak on this panel, to introduce a couple of solutions which are only part of the picture that we have that we are discussing in today's session. And I greatly thank Modus Foundation for the organization. Now we are going to review a little bit on a tiny little section of the whole CO2 reduction which is coming up in the future in marine industry. As my fellow speakers earlier have elaborated on the fuels for vessels which are at berth, for vessels which are en route, I'm going to look at what can be done to electrify short distance vessels like ferries, and what can be done to reduce CO2 when the ships are at berth, right? So we distinguish there a little bit, but before we deep dive into this topic, I would like to introduce you real quick to Stenman Technic. Our organization is located in Northwest Germany, and since more than 80 years, we are in the business of providing energy transfer solutions to mobile consumers. And these mobile consumers are typically locomotives, where we make the overhead current collectors, but we also electrify cranes and mining trucks and all sorts of other equipment in factories, for instance, where we need to transfer power, electric energy mainly, and data, anything from CAN bus, Ethernet, to the moving consumer, which can be rotating or which can travel in line. With some general industry trend to go electric, there was a new niche that came up, which was the electrification of electric vehicles. And since we are experienced in how to do that, it was a quick step to go from electrification of port cranes, as we can see them here, where we have provided the power cable reels and the spreader cable reels towards the new applications. So these new applications are ferry chargers for automatic connection, and shore connect systems, which some of you know as OPS, as onshore power systems, as land power supply systems, etc., etc. And we also do these systems not only in Europe, but worldwide. We are part of WAPTEC with a total of almost 30,000 co-workers in 50 countries. Now, what's the drive, the rationale for vessel operators to go electric? Well, Adam has mentioned it earlier, namely that on certain occasions where you have very short routes, it makes sense to go or to consider battery operation and battery energy storage as a CO2 reduction mean. Now, it's clear that electric power and onshore power only are a part of the fuel mix, but it can be a very vivid one, providing that the electricity comes from regenerative energies. It does not make sense to take a coal power station to donate the electric energy to a ship, because that's when you only shift the emissions. There is a big drive, mainly done by the International Maritime Organization, which is connected to the Paris goals to reduce CO2 in 2 different steps by 2030 and 2050, when zero emission is the goal. Very challenging because ships have this long lifetime, and ships which are built today should, in a best case, consider to be CO2 reduced or to provide the options, because these systems have a lifetime, the ships have a lifetime of up to 40 years. Now, there is also a pull from the market, namely that the for instance, for the ports, they are teaming up in order to urge the governments into funding of CO2 emission solutions. And the upcoming UN climate conference in October in Glasgow will see a paper and a call for action, which is handed in by shipping and port and terminal companies from all over Europe in order to reduce CO2. So there is a big background on going electric. Our role here today is to put the spotlight onto electrification solutions. But before we do that, it's clear that it takes a lot of leadership by the ship operator themselves. We have seen in the earlier discussions this morning that there is a multitude of different options. We can go electric, we can go on hydrogen, which is actually done by clients of ours. And we see that there's a big fuss of how-tos. So it takes experts, it takes naval architects, the terminal operator support authorities, the equipment providers, the shipyards, everyone to team up to find solutions here. At the end of the day, it is recommendable that the ship operator actually commits to this, because he, in the end, will have to live with the decisions that he finds suit his application best. The whole technology is rather juvenile, which creates a lot of concerns regarding the reliability and availability of the systems. And once you have made a decision and you go electric, like on a ferry charter, as we can see it here in Norway, you may face resistance from the public, because like in the United States, people don't want to go electric. They actually claim that electric ferries are not trusted. So they want to stay with their diesel ferries. And there are groups which peer up in order to fight this. So it takes a lot of resistance and a clear mind on going electric. Now, of course, water and electricity is a big challenge. So we have to make sure that the systems work in a fail-safe way. And to give you an example on how this can be done, I just wanted to indicate it here on this ferry charger, which is basically the lowest power supply system on the whole range or in the whole product portfolio that our organization provides. It can transfer up to 1.5 megawatt, either AC or DC, but it represents nicely that these systems are fail-safe. So what happens is they lower down after the vessel has safely moored. There is a Wi-Fi communication ahead of that to ramp up the systems. But in case the vessel is leaving the terminal for whatever reason, or when the movements are getting too big and the pilot contacts are being disconnected, then immediately we switch off the power, the charging power, and pull the whole thing back up by means of a spring, which is supporting the arm to go up again. So that is of importance to make sure that the operator, the vessel operator, the skipper, is always in control at any time. Obviously, environmental consideration need to be taken into account, but the sheer question of how do we want to charge, from the top, from the side, from a pontoon as it is indicated here, or from something that stands static on the pier, that is a long decision-making process, which can never be done within minutes or so. We have to take all sorts of operational constraints into account, the system integrator has to define the amount of power that is being transferred. And as I said, it can go up from 1.5 megawatt with these low-end solutions to 15 megawatt with fully automated connection. Why do we connect fully automated? Because on ferries, for instance, it is of key importance to have maximum charging time. Maximum charging time will reduce the size of the batteries, and therefore the total investment cost will make the ship more lightweight and therefore more efficient. Therefore, we defined that a ferry charger is always being operated fully automated with the safety features that I've just explained. And in order to help the operator to really make a business case out of it, we have seen that an electric ferry compared to a diesel or marine engine ferry typically has a strong business case because you can omit the engineer on board. So the crew headcount will be reduced just by the fact that systems are less wear and maintenance intensive, and at the same time, the jobs which need to be done on an electric ferry are done and fulfilled automatically. Short stopovers are key important, but in case you cannot approach a ferry from the side, like here on this ferry in Norway, we have considered solutions for terminals where you can only approach from the front, maybe from parallel of the pier. A solution that provides that is this new development, which is pretty much like a crane. It can be upscaled all the way up to 6 megawatt DC and also 10 megawatt in a high voltage AC application. And since the public is influencing the decision a lot, we have taken into account that we need to have a certain, let's say, appealing design on it to make sure that this new technology finds its acceptance in the industry. Usually these chargers stand in areas which are highly frequented, so they are seen by many people, and an ugly system in a nice downtown location from where ferries take off is difficult to accept. Now, to give you an idea of the flexibility of these units, we can run this little video here. I hope it travels well, and it shows that the ship side on the lower left is approached here in real-time speed. Of course, it takes only one of these arms, but a typical ferry operator would go for 2 different solutions on his end-to-end operation, also to provide a redundancy in order to make sure that the system is, that the ferry is operational even when one of the systems is, let's say, in the maintenance or not needed for whatever reason. We have developed questionnaires to really walk the client and the system integrator through all the technical questions which need consideration, and of course our design and engineering team backs this up. After installation, for instance, the whole project is being given over to the after-sales service to support the client with remote maintenance, with remote support, hotlines, etc., etc. Works pretty well. And I want to introduce you to a few of these family members to give you an idea of how versatile the systems can be. And indeed, we have here a pontoon, which is compensating the tide. If you cannot use a pontoon because the ferry charger stands on the land, then we have this vertical tower, which compensates up to 5 megawatt, or the bow ferry charger, which can compensate up to 8.50 meters of vertical tide, as we have it, for instance, on the North Sea, on the Pacific Ocean. In the Mediterranean, it's not that much, but the unit is pretty flexible to also charge ships with different berth. Here are a couple of impressions of a small ferry in Belgium, the first electric ferry ever there. and the Ampere, which is operated by Norlet. We have seen it earlier. I think it was in Gregory's presentation on hydrogen. Norlet is very leading edge on new technologies. Apart from the first hydrogen ferry, they actually were the first to electrify the ferry, and Stemann 6 years ago have provided the charger that you can see here on this picture. In the meantime, we are the sole supplier of medium voltage applications, which electrify the biggest European ferries, like the Bastofosen ferry between Moss and Horten. And also we have projects which require even more than a 9 megawatt of power transfer. We talk 15 megawatt automatic connection. Now, when we come to a wider application, then we are discussing solutions which we call shore connect. Other than on a ferry, which is where the main battery is being charged, the shore connect, the onshore power supply systems, help to switch off the diesel engine or ammonia engine or whatever, in order to get the hotel load through land power. Now, by switching the engine off, the iron of the engine becomes cold, and that's why this system is also known or referred to as cold ironing. For the different vessel sizes, we have provided different solutions, but the typical characteristic is that the ship is calling on a terminal for a few hours, so that manual plugging can actually be sensitive, can be facilitated and make sense. Pedestal type units like the one here on the upper left are applied in ro-ro applications, so for long distance roll-off ferries, which stay overnight, for instance, or for a couple of hours fixed on the dedicated terminal. That's where a fixed unit is can be used. For the Port of Gdynia, we have developed a system that meets their individual requirements on their ro-ros, which are pretty high up. So this arm would extend up to 12 meters because that's where the plug on the ship is. Cruise solutions, which have a very high hotel load, are being served with crane type of shore connection systems, which plug into landside connection boxes. These landside connection boxes stand, let's say, in a distance of 80 or 100 meters along the pier. And the mobile unit, which can be operated by one or maybe sometimes two people, travels to connect from the plug to the shipside socket. On the lower end of the food chain, we have the cable reels, which are very versatile, which can be handled by forklifts or cranes, go back and forth. To give you an idea of what a cruise plug-in station looks like, this is a magnitude of a cruise terminal like in Kiel on the Baltic, but also Rostock features the same system, and so does Southampton and Hamburg. This busy picture here indicates the solution at the Port of Kiel, where the AIDA Sol is being charged in this case. A wonderful solution which is compensating the tide automatically. You can see on this insert here that the cables are rolled out from an onboard cable reel, and then the ladder is presenting the plugs, which have a high weight of approximately 17 kilograms, are being presented to the crew. Now, to wrap it up, I would like to underline that there is a need for speed to reduce CO2 because of all the political requirements and the obvious impact that global warming has on our lives. Governments start acting, so it's the right time to review if funding is available, and we will see that the penalized CO2 emission in the future will make the business case for alternative fuels, and it can be electric, but it must not be. It can also be hydrogen, ammonia, and others. Becomes more and more vivid and justifies to take the action now. the units are used to meet the requirements of a niche. That's clear. If it works for you or not is something we can discuss in face-to-face meetings or in peer meetings in order to find the best solution and to justify or to find an answer to the question if this makes sense for your application. The commercially viable and proven solutions that are out there in the field, they sum up to over more than 200 that we have provided, and they range from 0.5 megawatt to 15 megawatt and beyond. We liaise with a solution provider as early as we can in order to find the best solution. And I think it makes sense to go for a couple of variations to meet especially the operator's needs. And that's my contribution to this seminar. I'm open for your questions, and here are my contacts. So please don't hesitate to contact me if you have any questions. Thank you.
Rainer, thank you for the informative and comprehensive presentation underlining the electrification and charging infrastructure and OPS solutions for ships and for ports, which is aiming to limit the emissions further. I would like to forward one question to you. It's coming from the audience. It's basically a rather technical question, but is it possible to combine two functions for this shore power supply installation? One of them at the same time to provide shore power for the diesel engines, which are at berth, and to charge the electric batteries for electric ships. So one infrastructure to provide these two options.
Yes, yeah, the answer is yes, and that is being done at present, for instance, in Norway, where we have seen operators which charge their onboard batteries, but at the same time they take like maybe 5 or 10% of the charging power to propel the Azipod thrusters. Now that gives direct energy onto the drive system. They have these electric Azipods which press the vessel into the terminal, and you can use that for let's say cooling reefers on board, for charging the battery, for providing hotel load whatsoever. The question is, how much power is needed in total, and that determines the type of system. So the answer is a clear yes.
Okay, and a short question from my side. I mean, we've seen early on so many solutions and so many future fuels in the mix coming up to give that perfect view of the future. But how fast do you think this we will see, for example, in the Baltic Sea or North Sea, these electrical ships and electrical ferries or feeder vessels with containers to basically ship around? Would you rather see it in a midterm or a long-term development?
It is so that mainland Europe clearly is a follower in this industry. We see that Norway has a lead with a total of more than 70 electrified ferry connections and potential for more. So for the followers, like the Germans, for instance, who are considering electrified solutions as well, there is no justification not to go electric because the system is proven. And we actually see that going electric is picking up. And we see a second trend, namely that the size of the vessels is growing enormously. Today, we are not only charging water buses like the one in Belgium. We currently have design projects which shall be delivered next year for ferries which carry 200 cars and 2,500 passengers and travel 30 kilometers. So the tendency is clearly towards higher distance and therefore higher power ratings. And I think the borders between electric propulsion and ammonia and hydrogen, they have neutral ground. So they are covering. Yeah, there's no sharp edge, but it will be very exciting to see in these overlaps what technology will be the winning one. But nobody is going for one solution only. Hybrid solutions can be discussed as well.
Yeah, excellent. Well, that's what we foresee as well, and we've seen from the presentations and summaries from DNV and from other leaders in this sector. So, Rainer, thank you once again for your comprehensive presentations on behalf of STEM and Technic. We are sorry that we are delaying the discussion panel, and we're slightly running behind schedule. But you all agree, I hope, that very interesting topics and discussions are ongoing here. So now I would like to move forward finally with our discussion panel today, based on logistics of green hydrogen fuel and based on the supply chain and production of green hydrogen-based fuels. And with that said, I would like to invite Mr. Bogdan Ołdakowski, the Secretary General of Baltic Ports Organization, who is going to lead the panel today and introduce the speakers and have a discussion on the topics. Bogdan, the stage is yours. Thank you.
Thank you, Emil. Thank you for inviting me to lead this panel discussion. And I have to say, I was listening carefully to the presentation, and I'm all the time learning, especially about the chemistry, how to change chemical energy into the energy that you can use on board of ships. But anyhow, I think we have to go on with the panel. And the panel is dedicated to talk about the logistics of green hydrogen-based fuels and how we are going to produce and probably also distribute, and what's the role of ports in whole logistic chain. So we do have panelists with us, and I would like firstly to introduce to you Maja Felicia Bentsen from Port of Rone, Bornholm. And in fact, we met yesterday with Maja in Copenhagen. And I'm just curious, Maja, if you are on Bornholm or still in Copenhagen?
I'm still in Copenhagen. I try to use the CO2 emission best possible when I do travel, so I always try to combine with more meetings when I'm in Copenhagen.
Thank you, Maja. Thank you. And a part of Maja, we're also having two additional speakers that you have already listened to: Adam Niklewski from DNV and John Kokarakis from Bureau Veritas. So we do have one representative of port and two representatives of classification societies. I think it's a good network, a good structure of people for such a discussion. So maybe I could start with the first question, which is about the future production of green fuels, hydrogen-based fuels. And I should start with Maja. Maja, I know that you have, on Bornholm, you have initiated some cooperation with your partners. And can you introduce this initiative? And can you say, how do you see maybe the production, or maybe your role as a port in logistic chain, providing these green fuels for shipping in the future? So please, Maja.
Thank you, Bogdan. I'll just try to. I have a very short presentation that I would like to share with you. I hope you can see my presentation now.
Yes, you can try to put it.
Try to get it in presentation mode.
Yes.
So very briefly about myself, as Bogdan mentioned, my name is Maja. I'm Chief Business Officer of the bulk business in Port of Rønne. Port of Rønne is located on the Danish island of Bornholm, which is in the middle of the Baltic Sea. I won't come too much into the fact that zero carbon fuels have a lower energy density. I think we've talked about that already. Also, the fact that ships will probably have to bunker more frequently. What I will instead talk about is that I see this as a business opportunity for Bornholm, which is located right here, just south of Sweden, north of Poland, and east of Germany and Denmark, mainland Denmark. And as you can see, there's a lot of vessels passing by Bornholm every year, 60,000, anticipated to increase to 80,000 a year. Which makes us an ideal location for becoming a green gas station in the Baltic Sea. And then we do have also a local ferry operator who's planning to transition to ammonia by sometimes in the second half of the 2020s. They will begin to run on ammonia, and this is also a preparation for this. So what we have done is that we formed a partnership called Bornholm Bunker Hub, where we, together with international partners, look at the entire value chain. As you mentioned, Bogdan, this is not only about consumption of zero carbon fuels on board vessels. It's also about being able to provide them to make the full supply chain work. So in our project, Ørsted and Halde Topsø and Rambøll is looking into the possibilities of having local power to X production, meaning producing the ammonia on the island of Bornholm. And then together with Bunker Holding and Bureau Veritas, we as a port are looking into how can we facilitate ammonia in the port, in future probably also methanol, if there's a market for that. And then, of course, the local ferry operator, Molslinjen, Bureau Veritas, and Wärtsilä are together looking into how can they then create this vessel that is sailing on ammonia. So this was very briefly on the project that we are working on. And you asked, Bogdan, about the production. I see a potential production on the island of Bornholm based on the fact that we have been appointed to be a Danish energy island with 2 gigawatt offshore wind production. So that could be utilized to produce some of this ammonia. And then, as I mentioned, I'm looking very much into, from the port side, looking very much into how can we actually support this transition? How can we, where at the port can we store ammonia in what quantities, and how do we ensure that we can bunker ammonia in a safe manner for the ferry once they choose to transition to that?
Thank you, Maya. I think you presented your concept shortly but very well, and I think you underlined that you are very centrally located in the Baltic, and of course you do also have plenty of existing and planned offshore wind farms in the Baltic. So
yeah, that's true. We will be surrounded by wind farms more or less on Bornholm.
Exactly. Yes. So you have at least 2 arguments to become such a point that you can really produce and bunker green ammonium. But I think you have more arguments like your governmental policy to establish the island of Bornholm as one of 2 islands in Denmark. Okay, thank you, Maya, for that. I could go with the same question to Adam. How do you see the production of green fuels in more general scale? Well, this production site would be located.
Yeah, so the answer is quite easy. What we could observe about the especially green hydrogen and green hydrogen based fuels, the principal concept is to build up the off-grid installation close to the source. So it might be, for example, offshore wind farms. It can be the solar farms with so-called hydrogen volleys, which we could observe nowadays within the Europe. And the same we can say about the e-methanol or ammonia, and maybe coming more detail about the e-methanol production facilities that has been launched recent days. The information that the Maersk is building up together with the Re-Energy e-methanol production facility in Denmark. The same has been announced in Norway. The company Liquid Winds will be operable for the e-methanol production facility, which will be able to produce 45,000 tons of e-methanol close to the coast. So that's the concept. The concept is what is the reason if we are talking about the hydrogen transportation. It is difficulties if we would like to use the pipelines on the longer distances, so it has to be compressed and transported in the tanks, either by the hydrogen carriers, if we are talking about the ships, either by the trucks, which are adjusted to this energy carrier. However, still, the main concept is to build up close to the renewable sources and mainly as an off-grid installation. That's what we could see nowadays.
Thank you, Adam. And a similar question goes to John. John, you are more from southern part of Europe. You know, in the north part of Europe, we talk a lot about wind energy, and there are lots of energy being produced from wind. Probably it's a bit different in Greece. You have more sun than wind. So is there any discussion about changing the solar energy into the green fuel energy? You have to unmute, John. You have to unmute, please.
This is a very good point. Although we have our share of wind renewable energy, we also have our primary source of renewable energy comes from solar panels, from photovoltaic panels, and this can be easily changed. And it is a major issue to connect the countries somewhat poorer in renewable energy resources with the ones that produce it. So this, we see production of green fuels, which is necessary because of the life cycle assessment. It does not make sense to emit more carbon dioxide to produce a fuel than what you save. So we see that in the future, transportation, either by ships or by pipelines, will take the green fuels from the place of production, from the supply chain to the demand point. This is especially true for hydrogen, which is working, is produced through a process highly energy consuming. The same is true for ammonia, but is also hydrogen is the main discussion. We expect to have a need of about 2,500 terawatt hours of energy from hydrogen by the year 2050. Evidently, every country will try to utilize any source of renewable energy that they have, either from hydroelectricity, from wind, solar, and whatever is available. But you're right, in the South Europe is primarily the solar power because of the highest connection with the sun. Like, for example, as it was mentioned by Mr. Altmeppen in the States, in California, in the ports, they utilize solar panels to electrify the ports of Los Angeles and Long Beach. And the reason that we can actually produce electricity and have the shore power connection the way that it is promulgated.
Thank you. Thank you. I think when it comes to solar energy and changing solar energy to run the ports, even in the Baltic, I think in Port of Stockholm, you have such installations in smaller scale also, I think in Port of Trelleborg. So not only in sunny California or southern part of Europe, even in the Baltic, you have some such examples. Maybe I have one more questions to you, gentlemen. What about the total efficiency of such a change from wind or solar energy into the hydrogen or ammonium? Usually, if you change the form of energy, you're losing some of the energy. So what's the efficiency of such a process?
Shall I answer first? If we are talking about the hydrogen production in the electrolysis process, it costs about 25% energy loss. So for example, if we have a 100 watts of the electrical power produced from renewables, then we need to minus 25 just for the electrolysis process. Then we have 10% more needs to be used for the compression, cooling, and eventual transportation. So that's the basic principles. And then after all, depends what will be done further with the hydrogen. Either you will like to process for the synthetic fuels, either you will like to use directly in the fuel cells. So if we use direct hydrogen, the fuel cells will nowadays have about the 60% efficiency. So it's end up with about the 38 watts at the end on the propulsion power if you also add the efficiency of the electric motor. So that's the very principal calculation on the efficiency using the green hydrogen, but maybe John will add some more on that.
I would like to confirm the numbers that Adam mentioned. I have in mind exactly the same numbers for the efficiency of electrolysis and to produce hydrogen. But I also have to point out that the solar panels are not very well known for their high efficiency. They have a relatively low efficiency in converting the energy into electricity of the order of, the last I know is around 15 to 20%. Of course, it's free energy, but still their efficiency is relatively low. So we base the exploitation on mass utilization as opposed to high efficiency. What is well known is that today's efforts are towards perfecting fuel cells, which inherently have a relatively high efficiency, because as you mentioned, every time we convert the energy from chemical to mechanical, from mechanical to something else, we have losses and irreversibilities. So the lower the number of conversions, the better. The numbers mentioned for the electrolysis, which is the main way to produce green hydrogen, and of course, hydrogen to be utilized in ammonia, are actually around that same number. What is critical to remember is that it does not, although ammonia seems to be a nice way to carry hydrogen, to liquefy, to compose nitrogen and hydrogen to make ammonia, and then to crack ammonia into hydrogen and nitrogen to take the hydrogen back, needs about the same energy like to liquefy hydrogen. So we don't gain much. The only thing we have is easier storage. With ammonia, we can carry it, crack it, get the hydrogen we need in a fuel cell.
John, thank you very much. I think it's becoming quite complex, all these changes, but thank you.
Can I add something here?
Yes, sure.
But thank you. I have a master's degree in chemistry, so for the efficiencies and so on, I can agree. I have also been working for a power utility about integration of renewable energy for 8 years, and I've been project manager in projects like this. And yes, you're right. We lose a lot of energy when we change electric energy into chemical energy. However, I would say, what's our alternative? If I look at the ferry operation that we have, for example, with a large high-speed ferry, RoPax ferry, it would be impossible to completely electrify that ferry because the weight of the batteries would be so significant that, well, it wouldn't be a high-speed ferry anymore. So on the consumption side, what is our alternatives? Because we cannot electrify the entire society. There are processes that we cannot electrify. I would also say on the production side, looking at renewable energy and solar is there when when the sun is shining. Wind power is there when the wind is blowing. At times we will experience that we have a huge overcapacity of production, much larger than what we can consume, and at other times we will have a low production from solar and wind. So in the end, I like to see this as a as an opportunity to actually win more energy, to be able to utilize some of all this renewable energy when it's available. So yes, it costs a lot of energy to transform from power energy to or electric energy to chemical energy, but I don't see we have any alternatives. And actually, I see that we also benefit our combined energy system by doing this.
Yes, this is a very important point, Maya. Thank you very much. I was just maybe rather curious what's the proportions. Okay, but I think the discussion is very interesting. But we have two another points to talk about. So now I'd like to go down to the port level. We have talked about the production and changing the energy from one form to another. But you know, among ports, there are discussions now how the ports should transfer for being fossil fuel ports to new hubs for new energies. And my next question would be maybe first to Adam and John. How do you see the role of ports in whole this picture, in whole chain? You have to have the production, but you then also have to probably transport those liquid fuels somewhere, and what the role of ports should be or will be. So maybe I'll start with John. John, you have to unmute.
The ports will be the connecting link between the places of supply and the places of demand. Hydrogen and the hydrogen-based green fuels, which was, as it was pointed out, will be produced in the near future, will have to be transported either with a fleet of vessels or via pipelines from within Europe or even outside Europe, like, for example, Ukraine or North Africa, and the ports will play the role of balancing the demand with supply. Evidently, they will have to change their master plans, as it was pointed out by Mr. Altmeppen, and I have to confess that his presentation was the first I've seen these nice chargers and actually the infrastructure for the cold ironing, which will be necessary and mandated by the regulations. Cruisers will have to utilize solar electricity. So the ports will have to change their master plans, their infrastructure, their machinery, and their vital links in this case. We cannot connect otherwise. I do not see a need for bunkering as would happen with LNG, for example, similarly to for hydrogen and hydrogen-based green fuels. Maybe not necessary at this stage, but it will be necessary to develop ports all over Europe that will proliferate the utilization of hydrogen and hydrogen-based green fuels.
Thank you. Adam, please.
Yes, so I will fully agree with John on that part. What I would like to comment maybe more on the infrastructure of the ports itself, because the current energy transition is giving a high flexibility of the fuels used by the shipping companies. So the ports definitely shall be ready to serve the different needs from the owners. And it's worth to mention that, of course, we have some of the infrastructure can be already existing infrastructure can be reused with very small investments. Like, for example, methanol can be stored in a common infrastructure for the marine diesel. But from the other side, the hydrogen or ammonia, that will be necessary to build up totally new infrastructure. The electrification of the ports is, in my opinion, out of the discussion. That is obvious that the process is ongoing and will be continued. So I would like also add two comments to the previous topics. First of all, if we are talking about the efficiency of the use of the renewable power, the direct electricity, we lost only 20% in total. So this is the very effective way. So on the shore coast shipping, the feeder fleets, the ferries, definitely that will be the direction which most of the ports will follow. And the secondly, what I'd like as well to add on my previous speech. Of course, if we are considering the hydrogen, mainly today we are discussing the consumers, the direct consumers, but it's important to also to mention that the hydrogen is considered as a kind of the energy, as an energy carrier, as a storage for this electricity produced from the renewables. So that actually also might be, if we consider this off-grid installation, the parts of the port hubs development.
Thank you. And Maya, the voice from your side, since you have already presented your concept, but what in details your port role could be in whole logistics of new fuels?
As mentioned here, we could, well, our role could both be to import fuels, some of these new green fuels. We could basically also be the point of export, because especially if we have power to X production, and as also mentioned here, yes, some hydrogen would be transported in pipelines, some hydrogen either directly as hydrogen or converted to ammonia as an energy carrier, as an energy storage, would need to be exported to other locations. And then you could perhaps say this is very, very low practical, but what I am doing at the moment is I'm trying to be the facilitator. I'm trying to make the different stakeholders talk together to ensure that we are ready once that the ferry operator is ready to use ammonia as a fuel. Because one thing is the vessel, another thing is ensuring that we actually have the storage facilities, bunkering facilities, and so on at the ports. So that is where I see my role at the moment, is to be a facilitator to ensure that this process actually happens, so that once we are ready, we are actually ready, that we won't be lacking parts of our supply chain once we say go now, we want to use zero carbon fuels for our vessels.
Thank you, Maya. Maybe this is a time when I can recall time when we have among the ports tried to develop bunkering facilities for LNG. It was like 10 years ago, and I remember very well that one of the key problems that we faced at that time was to really gather different stakeholders together and simply understand the whole process. And there were many challenges. One of the challenges we faced was that shipping lines, they are not really willing to express whether they are going for LNG or not. Of course, I understand fully, all confidentiality issues, but we couldn't really get the information how fast this process could happen from the shipping side. And another point was that also different authorities, administration around the ports, they didn't understand what LNG is and how safe or how risky it is. So it took some time, for example, to allow the bunkering of LNG and making the transfer of people from and to the ship at the same time. Quite many authorities at the beginning were against such a procedures. But that was just a comment from my side. Okay.
Bogdan, it's a very relevant comment, and hopefully now with hydrogen and ammonia and methanol, it has different properties, but hopefully we can learn a lot from the process of implementing LNG, so that we can speed up, so that it won't take 10 years or even I've heard even people saying it took 30 years to introduce LNG as a generally accepted fuel for the shipping industry, and we don't have 30 years for introducing zero carbon fuels.
You're very right. John?
If you allow me to make a comment here, being at the heart of shipping activity, as you know, Greece is at the top of managing world fleet, and discussing with ship owners in my position and with colleagues from other classification societies, it seems that the owners are in a state of confusion. They really wonder where to put their efforts, and I say this as an admonition as well. We need to focus. We are running to look at LNG as fuel, ammonia as fuel, methanol as fuel, hydrogen as fuel, nuclear propulsion, electricity. I believe we have to concentrate and define have a well-defined path, because people go all over the place. So everything is acceptable, but there is always the optimum. So to avoid this confusion, and as you know, in shipping, people do not like the pioneers. They expect the others to be first, and then they follow. So probably we need to focus. Hydrogen seems to be a good solution, or the hydrogen-based fuels. It seems that if we perfect the fuel cells, which is the way to go, because the internal combustion engines are not carbon-free with hydrogen and ammonia. We hear 30%, Wärtsilä mixes 30% in the blend to burn the ammonia. So what carbon neutral? It is not carbon neutral. Same for hydrogen. You need pilot fuel. I cannot tell you the percentage, but you also need carbonaceous fossil fuel to burn it. So let's focus and find the optimum solution. This is a key point from what I've seen.
Thank you. Thank you. Let's focus, but probably the question would be who should focus, who should lead that way. But this is a good point, and let me go to another question, the final question to you. The question is about Fit for 55. You know, the new proposal from European Commission, and how this package could stimulate use of green fuels. Probably the answer will be yes, but maybe at the same time I could ask you, because I can see that in Europe we're trying to solve that problem of emissions of greenhouse gases, but we are working regionally, and the climate change is a global problem, not the regional problem. So do you think, at the same time, maybe the next question is, do you think that the rest of the world would go similar way? Of course, we rather talk about shipping, but it is not only shipping. It's about whole global policy towards reduction of emission. So maybe I start with Adam now. The package Fit for 55. Do you think it will be effective? And how do you see the development of such a regulation, such a policies in global scale?
Okay, so starting from the first question, if the Fit for 55 will be effective, my obvious answer is nobody knows, because the taxonomy will be discussed and decided next year and enter into force in 2 years perspective. So now we have only the draft numbers. And if you remember the opening presentation from Mr. Pavelec, the rates given at this moment, they are not promote actually the energy switch to compromise the capex and the opex of the ship owners. That's one thing. The second thing, of course, yes, the direction is correct, and without any incentives, without any discounts, which owners can count on by switching to the low emission or zero emission fuels, this transition will not happen at all. So the question is first, what will be the final numbers? That's the first thing. The second thing, except the carrots, there are also plans for the penalties, which is in a concept on the energy taxation directive. So a combination of these two definitely will give the answers or the basis for making the decision by the ship owners. And one more thing, if we are talking about the Fit for 55, in my opinion, it is quite important, because if we are talking about the ETS, the trading of the emission, we consider the emission tank to propeller. But if we are looking into regulation framework for the fuel EU maritime, they first time consider well-to-wake emissions. So that's open up the big bag of the biofuels, which can be treated as not either the emission-free, but also to the emission consumption fuels. So the picture is quite comprehensive, I would say. And answering your second question, definitely Europe, North America, and Greater China. This is the forefront of these changes, and that will be the three big markets, three big consumer and the player which will influence, I believe, the other parts of the world.
Thank you, Adam. John, please.
Yes, very interesting question. Of course, my personal opinion is that this type of very important step towards decarbonization should actually come from the global world regulator, which is the International Maritime Organization, IMO. So my personal opinion is that this type of regulations should come and be voted by IMO, because if Europe goes ahead with Fit for 55, we're going to see following up similar regulations from the United States, then from China, and the question is, where do you stop? We have to admit, though, that the Fit for 55 package, although it favors biofuels, which are not exactly carbon neutral, and LNG, which has been blamed as polluting because of the methane slip, still we see some hopeful and nice regulations. Like, for example, it requires 50% of the non-biological origin renewable fuels to be utilized by 2030. In addition, they ask for about 2.3% share on the renewable fuels to be utilized in transportation by the same year. So this is a nice step forward. The regulation, the package includes the need for hydrogen refueling stations throughout Europe, which is also a good step forward. But there are now, regarding the effectiveness of the package, like Adam mentioned, it remains to be seen. There are other opinions favoring other market-based measures, like, for example, to put a tax on the fuel, certain levy, which would be actually automatically, the money would be utilized for research in the area of decarbonization. But at the same time, let me point out that in the recent MEPC 76 that we had last June, the Assembly did not vote for the $100 levy proposed by some countries. So it is not easy. It's an ongoing discussion. We will see what happens. Still a proposal in the Parliament. Let's see if it's going to be voted.
Yeah, for sure. There'll be a hard discussion in Parliament and then in the Council, European Council. So Maya, please.
I think EU Fit for 55 is very beneficial. There will always be debate. I think no matter which regulation or legislation you make, regardless of the area you make it on, you will have, it cannot be perfect. So yes, we will see some trading patterns change because of EU Fit for 55 at the borders of EU to try to sneak around the regulation established by EU Fit for 55. But I think if we don't have EU Fit for 55, if we don't go ahead and say we need to do something, then I mean, somebody have to take the first step, even if the first step is perhaps not the ideal solution. And what is the ideal solution? And then I'm also very happy to see that besides EU Fit for 55, this call for action that 150 industry leaders from the shipping industry have now taken and said, we need to have some sort of regulation so that we can decarbonize this industry. And who knows, if we hadn't had the EU Fit for 55, if we haven't had that push from, well, it is one of the larger shipping areas in the world, right? So if we hadn't had that push from EU Fit for 55, who knows if this call for action would have actually happened. And perhaps this call for action could be the next step towards that this becomes something that IMO is working with, which is, yes, it's where it's supposed to be in IMO, but for different reasons that hasn't happened. So then somebody else have to step up and say, now we do something. So I think it's very good that we have the EU Fit for 55, even though that it will be a challenge for us at the port, for example, to be ready to live up to these regulations put up by EU Fit for 55.
I completely agree with you that it's very good that the European Union is paving the way for other regions in the world. And of course, IMO is a bit conservative and slow organization. There are many governments around the world, and it's not that easy to start the process. But I can also see that some of the consequences of the Fit for 55 would impact the competitiveness of European ports comparing with third country ports. And there's no time for detailed discussion, but you know, if you're trying to solve the global problem regionally, you always would impact the rules in the region that would make some disadvantages for these rules for this market comparing to other markets that is next to you.
That's very true, Bogdan. But who says that nothing will happen in IMO within the next 9 years?
Well,
I mean, the world is changing very fast. So who knows when IMO will also pick up? I'm quite confident that they will pick up sooner, so that there will also be some sort of global regulation in place for 2030. I cross my fingers at least.
If I can comment on that. I'm not the IMO defender, but it has to be said. We have EXI and a carbon intensity indicator index come into force with the effective date of 1st January 2023. So on the IMO level requirements, the movements are done, and the next reflection is planned to be in 2027 based on the collected and analyzed data. So definitely there is some moves on the IMO level, not only the well-known IMO GHG ambition, but with the real requirements. So it's not fully true that there is no moves on the IMO level on the decarbonization way. Yes, John, please.
Further to this, we'll open a big discussion now, but the new regulations, the CII and the EXI, sometimes it is not effective to have regulations under pressure, especially when they do not come in parallel with technological maturity and development. And we see this problem with the CII and EXI regulations. There are studies. There is a study actually from Danish Technical University, which discusses how this CII will be varying in the future. and they say it's practically impossible to have convergence. We talk about X% reduction every year. We are not going to see a converging solution. So it is not going to be useful for the future. This is the prediction from the paper, and I do agree with it because of the factors associated with the ship operation. So Denmark took the lead in this case and proposed to apply this regulation not on specific ships, on a vessel, but on whole fleets. And this would have been a solution. But we will see what will happen in the future. I will agree with the panel that it is not easy when you have 150 plus countries in an organization. It's not easy to have everybody agreeing. It's like a painful exercise during all these MEPC discussions.
Thank you, John. I think we have to conclude shortly. And my question to you, do you like to rise or give a final comments from your side? Maya, do you have any final remarks from this panel?
I don't know. I think this is a really interesting topic. I love to work with it. And I'm very curious what the world will look like in 10 years' time.
Thank you, Maya. Adam, any final remarks?
Yes, just 2 words. Definitely we gained the momentum of a change, and that's from one side it's very challenging, and from the other, as Ms. Maya said, this is very interesting and fascinating time. So we'll look for the future, what will bring and what the solution will be actually chosen. And from my side, I'd like one more time to thank you for invitation and for the nice discussion at the panel. So I really appreciate and thank you very much for invitation.
Thank you, Adam. And John, any final comment?
I will say it in Polish. Dziękuję bardzo for the invitation. So it was a very interesting discussion. I believe we're going to see in the near future a continuous discussion and about these regulations. And I believe we are going towards the correct direction. That is fueling and getting energy from renewable sources. Thank you.
Thank you, John. From my side, I would say that Baltic ports would, of course, play its own role in this development, and Baltic ports for sure will not be a reactive body. We will try to be a proactive in whole process of decarbonization of maritime transport. Okay. Thank you all for being with us. And now I think I hand over to Emil, please.
Yes, I will have to say thank you, Bogdan, for leading this very exciting panel. Really lost track of time, but very key topics were discussed. We're going all the way from the green hydrogen-based fuels to the other energy solutions and solar and wind. Obviously, we need more time for such a panels. We will consider next time to extend this type of discussion panels. Very insightful. Thank you once again, Bogdan, and to Maya, Adam, and John. So, with that said, we are concluding today's webinar. I would like to just mention a few sentences to summarize, but obviously we get such an insightful panel that I'll just highlight the key topics. Well, green hydrogen-based fuels being an important part of the European Green Deal and Fit for 55 EU package will be part of the solutions in the future demand. Hydrogen is seen as the main decarbonization alternative in the maritime transporting sector. We've seen by 2050 some of the predictions, and DNV mentioned as well in their report the dominance of oil in the fuel mix will be displaced by these zero carbon fuels like ammonia, hydrogen, and other electro-based fuels. Hydrogen is a major contender, but according to some of the DNV forecasts, it's not foreseen to supply more than 5% of the global energy demand. Let's hope they will be able to see by then what it will happen. 5% is a bit low for me, but let's hope for more. Ammonia has been underlined as one of the fuels of the future due to the advantages. It's as a shipped commodity and it's cheaper to produce and easier to store. We've seen as well that electrification, charging infrastructure, and OPS for ships represents an important solution in the mix to limit this pollution and emission caused by auxiliary engines of ships. Well, as I said, discussion panel was very insightful, highlighting the future production and supply chain and logistics of green hydrogen. We discussed as well the other renewable energies in the ports and in general for this sector. So not to keep you any longer and delay, dear colleagues, today we have attendees from all across Europe and beyond even. Excellent presentation by our speakers with key findings and estimations. Very good discussion panel. And we hope you find the webinar very insightful and helpful to open some new perspectives for you. Thank you once again to the presenters and to the event partners. Thank you for joining us and hope to see you all soon. Thank you.
Thank you, Amin.